Okay, we're going to be doing validate binary search tree. It's a popular problem at Facebook, Apple, Bloomberg, Microsoft, definitely Amazon. So you're given the root of a binary tree and determine if it is a valid binary search tree. A valid binary search tree is defined as follows. The left subtree of a node contains only nodes with keys less than the node's key, in other words, values. The right subtree of a node contains only nodes with keys greater than the node's key. Both the left and right subtrees must also be BSTs, right? So here we have 2, root at 2, 1, and 3, right? Essentially what this is, the solution is very simple. If you do an in-order traversal, right? If you do an in-order traversal and the value you find is while doing you can store these results into an output, right? After using in-order traversal, and then if they're sorted, right? Because in-order traversal of a BST results in a sorted array, right? If you do in-order traversal on this, you'll get, because in-order traversal is left, root, right? So left, let's actually do it here on the side so that you can see. Right, hold on a second to plug my display in. Okay, so we have this tree, right? It purports to be a BST, but we don't know, right? So let's use in-order traversal. Remember, in-order traversal is left, root, right? So we start here, we're at the root, we go left, right? We come here, we go left, it's null. So we come back here to the root. So we've done this, which is left. Here it was null, so we didn't put anything. Root is 1, we place it in. And then right here is null. So we come back all the way here, back to root, we place root in, 5. Then to the right. To the right, we come down all the way this side to the left, right? So it's left here, 3, root, 4, right, 6, right? And then we terminate. So this is our output. When we check, our output is not sorted. Why? Yes, all these are less than 5, but then here 5 is greater than all to the right, yet it's supposed to be less than all to the right. You see that? So 5, this side is fine, this side is fine, but this side 5 is greater than all except 6. It's greater than 4 and 3, right? So let's do a simpler one, right? In-order traversal. We have 2, 1, and 3, right? So we start, remember it's left, root, right, okay? So when we go to our left, and we check here null, we come back here, root, which is 1, we come back here null on the right, then we come back here, which we already did, and then we come back here to the root again, 2, and then we come back here to the left, it's null, to the root, 3, to the right, null, 1, 2, 3. We can see that this is sorted, so this is a BST. Another thing is here, we need to consider the fact that there may be duplicates. If there's a duplicate, then we don't consider it a BST, right? So let's code it up, right? So it's a valid binary BST if after in-order traversal, we have a sorted array. So what we're going to do is we create a function that does in-order traversal of a tree. So depth in order will take our let's call it node, and then we'll call it store, right? Store will be our store for which will place the values in, and then node will be traversed, right? So how do we do in-order traversal? It's left, so if node dot left, then in-order node dot left and store. Then root, which is where we are at, node dot val, which we're appending to store. Store dot append node dot val, and then write. If node dot write, then in order node dot write store, and that's it. We're done with our function. So now we create an output to store our result array. So we'll call it output is equal to that, and then we call our function. Which will be in order with the root and output, right? So our output now contains either a sorted or non-sorted array, and we check. How do we check? For I in range, we're going to start from, okay, we're going to start till length of output -1, right? The reason why we're doing that is so that we iterate from this portion to here, and we check whether this and this and this, all right? So that's why we stop at the second last position, so that we can compare. So if output at I is greater than or equal to output at I plus 1, right? So that's why we had to stop at the second last index, right? Remember, Python stops one index before what you put here. So we wanted to stop at the second last index so that we can do I plus 1. So if it's like that, then we return false. Otherwise, we return true, right? And voila, it works. It works. That's it. That's the solution. And this takes O of n time, and the space complexity is O of n as well, right? Because on the call stack, you're going to use up n, and as well on with the output, you're going to use n. So this is a solution. Yes, I got 84%, but the one way I can think of optimizing it is somehow initializing this output and then comparing the result, right? Yeah. So yeah, so you can reduce this to 1. But even if you reduce this to an O of 1, you still have the call stack, which will be O of n, or if you used an iterative solution, you're still going to be looking at O of n, because you'll have to place them in, like, say, a queue, or you'll have to place them in a queue using BFS or a stack. So the solution, this is the solution. So thank you and bye.